Hello friends, welcome to VK Lectures. In this session, we are discussing the Miller indices from solid state physics. Miller indices. Now, Miller indices are set of parallel lines, set of parallel planes which are equidistant. So the planes makes intercepts in x, y and z axis. So Miller indices is proportional to the inverse of intercept. So the values h, k and l are a by OA, b by OB and c by OC. Now A, B, C are lattice constants or lattice parameters, and OA, OB and OC are intercepts along x, y and z axis. Now the equation of the plane is given in terms of the HKL and the intercept. So equation of planes or the plane that makes the intercept or the which gives the Miller indices HK and L or the intercept OA, OB and OC are x by OA plus y by OB plus z by OC will be equal to 1. Now in terms of HK and L, which is hx by A plus ky by B plus lz by C equal to 1. So this is the equation of the plane in terms of the intercept as well as the Miller indices. Here we have a concept called density of unit cell. Now assuming there are m number of atoms, so n number of atoms in a crystal, and the mass of the, let me write the total mass as equal to m, and let me write the number of atoms equal to capital N. Then mass of one atom as will be equal to capital M by capital N. Now volume of the unit cell, the unit cell will be equal to A cube, and number of atoms in unit cell will be equal to n, small letter n. Then mass of unit cell will be equal to number of atoms in the unit cell and mass of one atom, which will be equal to m by n. Then the density of the unit cell, rho is equal to total mass by volume. So mass of the unit cell is given as n m by n divided by the volume, which is a cube. Okay, so we can write this is equal to rho, so a cube can be written as n by rho into m by n. So this is the formula connecting the lattice constant and the density. Okay, now for simple cubic, the value of n equal to 1. For body centered cubic, it is n equal to 2. Face centered cubic, it is 4. Base centered cubic, base you will write base centered cubic, it is equal to 2. And for HCP, it is 6. The angle between two crystal direction. Here let us assume this as our crystal, and here you have two planes. We are asked to find out the angle between the two planes. So this is vector A, and here you have the vector B. Now the vector A can be written in the form of the Miller indices h1 ax cap plus hk1 by cap plus l1 cz cap. Similarly, the vector B equal to h2 ax cap k2 by cap plus L2 CZ cap, and we know that A dot B equal to magnitude of A times magnitude of B times cos theta. So this can be written as cos theta, or you can write here cos theta as equal to h1 h2 a square plus k1 k2 b squared plus l1 l2 c squared divided by root of h1 square a square plus k1 square b square plus l1 square c square times root of h2 square a square plus k2 square b squared plus l2 square c squared. Now if the lattice is a simple cubic, where you can write a equal to b equal to c, then cos theta will be equal to h1 h2 plus k1 k2 plus l1 l2 divided by root of h1 square plus k1 square l1 square into h2 square plus k2 square plus l2 squared. So this is what is the cos theta term gives you. Here we have another concept called interplanar separation. So this is interplanar separation. Okay. So now this is our plane that is given in yellow color, and this is the z-axis, and here we have the y and x, and this is the center of the center, and ox, or this distance, let us mark it as a, and this as b, and here you have c. Now OA, let it be small letter a, which is the lattice parameters. Okay, then from OB we have b, and the OC, which is written as small letter c. Now here we can write OA equal to a by h, which is the Miller index, into x cap, OB equal to b by k into y cap, and OC equal to c by l into z cap. Okay. Now how to write the equation of the plane? We can write it as hx by a plus ky by b plus lz by c equal to 1. Now the gradient of the plane phi equal to h by a into x cap plus k by b into y cap plus l by z into z cap. So this is the del phi, and the magnitude of del phi is equal to root of h square by a square plus k square by b square plus l square by c square. So this is the del phi, the magnitude of del phi, and this is del phi. Now del phi will be projecting in the direction which is perpendicular to the plane. Okay, so now the projection of OA, the vector OA on n cap. Now what is this n cap? N cap is the perpendicular direction. Okay, n cap gives perpendicular distance. That means the distance from this point to this, or you can write, if this is the point from center to this point, will be given by the projection of OA, which is nothing but the distance of plane from center. Now, so the DHKL, so which means the distance HKL for orthorhombic crystal. Now, what do you mean by orthorhombic? A, B, C are not equal. Orthorhombic crystal. So this is equal to 1 divided by root of h square by a square plus k square by b square plus L square by c square. Okay. So what is orthorhombic crystal? A not equal to B not equal to C. So this is the what you have to remember from this particular slide. So for interplanar separation, DHKL, this is for orthorhombic crystal. We have the value of the interplanar separation is 1 divided by root of h square by a square plus k square by b square plus L square by c square. Okay. Now, if the crystal is cubic, for cubic crystal we have DHKL is equal to A divided by root of h square plus k square plus L square. Now in the case of cubic crystal, we can write A equal to B equal to C, and this one equal to, you can consider it as equal to A. Now again we have another type of crystal, that is tetragonal. The DHKL value, DHKL as equal to 1 divided by, now before going to the formula, what is tetragonal structure? Here A equal to B not equal to C. So DHKL value will be given by the formula 1 divided by h square plus k square divided by a square plus L square by c square. So these are different interplanar separations in orthorhombic, cubic and tetragonal structure.